Zuria, I've given you recording permissions. So
Okay.
can you see the record button now?
Yep, it's recording now.
All right, go ahead.
Awesome, thank you.
See you. So should we just wait a couple more minutes for other people to join?
Sure.
Let's wait till 9:10 or 9, just to be safe. Ah, another person. Okay, Philippe joined.
Philippe, yes, Philippe did join. Good. He's one of our undergraduates here.
Okay.
Working with Dr. Furong. They're actually characterizing your powders that you sent. They're running catalysis experiments on them.
This synthesis and the first wash should only take maybe an hour and a half to 2 hours at most.
Okay.
Yeah. I also don't want to make the recording too long, or else the file will just be too big. There'll be a lot to get.
I'm thinking maybe we can go back later and edit it. You know, cut out the.
Yeah, sorry, I wanted to ask, how was the SOP I sent you?
Oh, it's super easy to follow. So yeah, that was really great. Thank you for that.
Do you already have the chemicals you ordered for the synthesis?
Well, I haven't received them yet, but the purchase orders were sent out. It seems like hexane and the ethyl acetate are your greatest consumptions, huh?
Yeah, you'll need a lot of hexane and ethyl acetate for the washing steps. So
have you tried any other solvents? Like somebody suggested to me that chloromethane.
Yeah, chloromethane could be a good choice. My experience is that the hexane ethyl acetate does the best combination.
Okay. And also I was thinking maybe like one of my colleagues suggested, why don't you just get like a distillation kit and just reuse the hexane, like distill it out and reuse it. And I was like, oh, that sounds like a good idea, because if not, we'll be spending like over $100 of hexane per run.
Yeah, that's also doable.
Yeah.
Although in our case, we just happen to have so much hexane in our lab that I was just using them.
Gotcha. Okay, oh, that makes sense. Yeah, my boss is like, oh, why are you ordering so much hexane? I think we have some. I'm like, we do have some, just not enough.
Yeah. All right.
I can continue to let people in the room as well.
Okay, so I guess we should just get started. I mean, it's already 9:06. No one else is showing up. You know, as people trickle in, Jacob can let them in. All right.
Okay.
So it's a really simple setup of synthesis. So all you need is the 100 ml beaker, the thermal, and then also you need just a 1 liter open layer flask. This will be your main solvent flask. This is what you're going to use to pour your ethanol solution into the separated form. So in this, I'm going to put in the ethanol, the tetramethyl ammonium solution. This guy. Oh, sorry, guys. We had troubles with this steel for so long. Okay, so I'm just going to leave that there. So this is what you want, Zuriel, the tetramethyl ammonium hydroxide hydrate. This will be what you put in the ethanol solution. A little concerned I may not have enough 6 grams here, but I do have another bottle. So we need about 6 grams of this guy, based on the quantities I wrote for you. sometimes it's not pretty hygroscopic stuff that's sticky. There we go. Now, we have 6 grams. There's 4 here. So now that we have 6 grams, ethanol, you want to add 60 milliliters. I prefer doing it by mass, it's a bit more accurate. Instead of 60 mils, I'll say I'm adding 47.34 grams. So if we go back to scale here, and by the way, Zuri, I want to mention, synthesis I'm doing is the 15% nominal doped cobalt. So this would be the 15%. So now we're getting close to 47.34, which will be about that. All right, good. So we have about 47.34 grams now. So this is ready to go. This is our ethanol solution. We'll stir this layer. Now, in our main reaction class, we're going to have the zinc acetate and the cobalt acetate precursors, and the DMSO solvent will be added here. This is too big for the scale, so I'm not going to measure here. I'll measure everything here. So since I'm doing a 15% dope, I want everything to be a 0.101 molar initial concentration. I'm going to have to use 3.392 grams of the zinc acetate precursor and 0.679 grams of cobalt. So let's do this in. So we have a zinc acetate dihydrate right here. This is our main zinc precursor. So we have about 3.392 grams. Okay, good. So we have about 3.392, 3.4 grams of this guy. We can add to the bromide. I'll reuse the same weight paper because the cobalt's getting added to the same class anyways. So just help save. We're done with the zinc acetate. We have all of our zinc. So now, what I'm going to be adding is the cobalt dopant. You need cobalt acetate tetrahydrate. It doesn't tell you the full name up here, but it does give you the chemical formula, which I also put in the SOP. You can see you need cobalt acetate. This one we need about 0.67 mils. Oops, 0.67 mils. And we'll also add it. So now in our main reaction class, we have the zinc and cobalt precursors. The DMSO, we'll be adding that with the graduate silver. So now everything here. For now, I'm just going to bring all my stuff to my lab. So let me go ahead and just get my other stuff, and I'll be right back here. Stay here for now.
Okay.
Okay. So this step, now that we have the ethanol solution ready, we have our precursor in our flask. All we have to do now is just add DMSO, the dimethyl sulfoxide. So it's a pretty big container around here, but dimethyl sulfoxide, DMSO. This is the main solvent that we're using for our synthesis, right? It's the most important guy. So for the doubled up reaction quantities that I listed, we need about 198 grams. That translates to 180 mils, right? So because we need such a large volume of it, I'm going to pour it twice with the graduated silver. Oh, sorry. I forgot to get the bottom. Here. So we want about 100 mils. I'll pour about 100 and then I'll pour about 80. Sure. That's good. Under there. I still need 80 milliliters. Here. Yeah, 180. Right. 180. Drop in there, so that's fine. Just I'll pick that up. And now we have 180 mils added. All right. So now we have a solvent added. It should turn like this pinkish color when all you have is a DMSO. All right, you haven't added your ethanol solution yet. So let this go around for a bit. We kind of want to break up some of the aggregates a little bit. swirl it, and then what we'll do is we'll turn on the magnetic stir plate. This guy. We'll let him stir a bit. You also want to stir this guy. So let this guy stir for a bit. You also want to stir the solution that we're going to have. While he's doing it, now we have to add the separator funnel. All right. This is what we're going to be using to add the ethanol solution here, dropwise, right? And I have to emphasize it should be done dropwise because you want to make sure that these get completed at a steady pace, right? Do you have any questions so far? Yeah, Zuriel, please. Do you two have any questions?
No questions for now. You're doing great. Thank you for narrating and.
I kind of cheated.
Is the color importance from the salt?
Yes. So if you don't get a color like this, it means, at least for 15%, it means you did not have the right ratio of the dopant to zinc precursor, or you don't have enough of the solvent. So it should be like this purplish fuchsia violet color, something like this. If you're doing the 15% cobalt, if you increase the amount of cobalt, it'll become much more blue greenish as you increase the concentration. I kind of cheated. I already got this folder ready. So what you want to do is, okay, I kind of want to get this.
Well, you just don't FaceTime, man.
We're gonna funnel here. Okay, so we kind of want to do it like that.
What?
So you have
No, I actually did it.
Oh, sure. Questions? Okay, good. So yeah, you see now that we're breaking up those aggregates, so now it's dissolving more of the solvent, so now it should get a richer purple color. In the meantime, while this is stirring,
Are you done?
set up the separator funnel. You want to make sure, most important step, make sure this is horizontal. All right. If this is horizontal, it means we have blocked and stop pump. Nothing's in the air. If you have it vertical like this, parallel, then that means everything's going to trip right through, right? So make sure before you add the solution, the separator funnel, it's horizontal like that. All right, so we're going to let this go for a little bit longer. You want to let this go for a little bit as well. Give it about maybe a couple more minutes. These should dissolve. Any questions?
So how slow are you drop
You want to be able to
casting this?
see. Right, you want to be able to see individual drops. So I'll show you as we do it. You want to adjust it very slowly, and you might overshoot it a little bit, so it starts dipping a lot. Then you go back a little bit to see like individual drops going down.
Okay, I actually ordered a titration burette for this part because I felt that would give me better control over the drop wise.
You can use separator funnel, titration bureau, anything that gives you that control over the addition of the solution.
Okay, great.
And sometimes if it doesn't fully break all the way, what you can do is,
Are you heating the hot plate?
no, this is all done at room temperature. So we can shake it up a little bit like this, just to break up those aggregates. And then, back down. So let that sit there, and we'll turn it back on. And then we'll put this back here, right? So every now and then, even as you're doing the addition, I recommend swirling it a bit every now and then, just to make sure it really spreads evenly as you add the solution. All right, we'll see that step as we do. So we look here. This is more or less dissolved everything. So this is kind of safe to add. Now, don't worry if the stir bar falls here. The stir bar, even if it falls in here, it won't be able to go through the hole. So if anything, having the stir bar block the stop pocket bit might actually give you better control. But if it does fall through, don't worry about that. So again, make sure this is parallel, so it's blocked before we add. So now we're going to add this. You want to see, so yeah, stir bar still there. And again, if it does fall, don't worry. Right. Okay, so it dropped for me, but that's perfectly fine. This can't fall through; it's too big. So now we have our tetramethylmonium hydroxide and ethanol solution here. We have zinc acetate and cobalt acetate precursors dissolved in DMSO here. Now is the actual reaction. We're going to actually add step one. So again, I have to go very slowly here. I want to make sure I don't go too fast. Like that. You want it to be about this. So you can see individual drops. And if you pay attention to the color is going to start changing. Also, shake it a little bit. So as we see, it's starting to go more dark blue now, and purple disappears. So you see now the cobalt starting to integrate into the zinc oxide lattice. And so now the cobalt, because it's integrating to that lattice, we're getting those absorption features, and cobalt's uniqueness. That's responsible for the blue color. So you see, tell so far, Zuriel, this synthesis is very simple. It's done in air and it's done at room temperature. So those two facts alone make this a very, very easy synthesis to do, to replicate, even to scale.
You're doing this under a fume hood always?
Yes, always.
Okay.
Yes, you're correct, Zuriel. It's going to be white, regular zinc oxide. So regular zinc is a D10 system. And so it has no absorption features in the UV disc. So all you should see when you do absorption on this is just a flat line for the most part. But then you'll see the band gap of zinc oxide like 330-ish nanometers. You see now it's starting to, purple is starting to disappear and get more blue.
Do you always want your solution to be stirred vigorously?
Yes. So let's see here. So the rate of stirring doesn't matter too much. I just prefer going vigorously to ensure it spreads evenly throughout the whole solution. And because this is a room temperature synthesis, the kinetics are very very easy to understand. Very nice. Dana, who was one of Daniel's first lab students, she invented the synthesis. And it has played a huge role in helping to scale up the Oxide.
I believe Dr. Banerjee posted a question for you. If you could answer, please.
We want to scale. So Professor Banerjee, it's always good to keep the initial precursor concentration the same. That affects the mutation and growth of the nanocrystals, but you can't scale everything accordingly as long as that initial metal concentration is be right. What I did for this instance is I doubled all the quantities that Dana used, and that's how I was able to get about 1+ gram. Oh, the volume. Yes. Correct. So if you just double the volume, then you'll lower the concentration. That'll lower your reaction kinetics. So that will influence the growth of the different animals. Yeah, so Professor Banerjee, just scale everything for you. So if I want to double my production, I double all the quantities I use. If I want to triple, quadruple, then triple and quadruple all the quantities. So as you see, everyone, now it's getting this nice, I guess, outer space blue color. So this is how you know the cobalt really does substitutionally go into the zinc oxide for this. Okay, so now it's kind of done. I'm just going to go all the way, just get a residual amount. So as I kind of said before, if the stir bar does fall in here, don't worry about that. If anything, as I said, it might actually help you with the control, because if this wasn't there, this would be a lot more sensitive to controlling the rate. But anyways, now that this is going, we have all of the zinc oxide nanocrystals condensed in DMSO. So if you know our relative polarity very well, DMSO has an exceptionally high relative polarity. So to crash out these nanocrystals, we have to use something much more non-polar by comparison. The good candidate I use is ethyl acetate. This is a good anti-solvent relative to DMSO. So this will crash out your nanocrystals. So what I'm just going to do now that this is done, take this off. And we'll go a bit more. Okay. We can now add ethyl acetate. So my general rule of thumb, I like having a good 3 to 4 times the amount. So I like going to about 800 mils here for adding the anti-solvent. So this will ensure we have enough to crash out everything. So now, just to recap, the synthesis is done. We have synthesized our nanocrystal. This is the entire synthesis right here. Everything I do from this point onward is just work up and cleaning the nanocrystal. That's it. All right, so I'm going to show you the first wash step right now, and that'll be the ethyl acetate DMSO wash. So remember, all the nanocrystals we made are contained in this DMSO solvent. We want to clean and crash these out as we do the ethyl acetate washes.
Is there a static amount of cobalt we need to drop, or do we just watch for the color change?
So it's mainly the color change. That'll indicate you have the correct building to minus. For the rate, Dana wasn't specific. She did mention if you do a drop rate speed. Jose says the same thing. When Jose did the synthesis, he ensured that it's moving at a specific level. Sure. So now that we've kind of stirred this for a bit, it's going. And I'm gonna go to about like 800.
Does it matter if you pour it slowly or not?
No, because the synthesis is done. All I'm adding now is the anti-solvent. Okay, that should be right. So I have about 800. So now we'll just let it stir. The anti-solvent goes in there. I'm going to get 8 Falcon tubes. So this is the centrifugation step. I'm going to crash out all the nanocrystals, get the solid at the bottom. We're going to have to do it twice to make sure we get through all of this. So if we have 850 mil Falcon tubes, then 8 times 5, that should get 400, right? But I have about 800, so I'm going to do about 2 runs. So something like this. Falcon tube right here. 8. Okay, now we are done. And believe it or not, this workup step actually takes up the majority of the time. See, this is very simple. It goes super fast, but all the washes and crashes you have to do, that'll take the remainder majority. For now, I'm going to move these bottles up and leave it anymore. So I have about 800. I want to pour about 50. So remember, this is the solution with the nanocrystals, but it's also with anti-solvent. All right, so what the anti-solvent does, it's going to flocculate out the nanocrystals and crash them out. So as these credits sit there over time, that's what's going to happen.
Do you think there's a way to do it without centrifugation, like just evaporating all of that out, leaving the nanocrystals?
So you have to remember, DMSO, you know, its boiling point. DMSO's boiling point is around 200, excuse me, 180 something. So, yeah, so I would recommend washing off all the DMSO first. There's a reason we do the second half of the washing step, which is hexane ethanol. But I'm only going to show that first washing step, so you know how to do centrifugation. And that's to make sure that we wash off all the DMSO. And all we have in the nanocrystals are the hydroxide ligands. So when we do the second step of washes, we'll have just ethanol hexane, and that'll be much easier to try out.
Okay, that makes sense.
The DMSO is a great polar electrode solvent, but anything involving drying with DMSO is going to be an absolute nightmare.
Do you think there are unreactive precursors getting washed away too?
Any unreactive precursors? No. So if this synthesis is very fast, so all the precursors should have been. It's very It's going to take quite a while, so our centrifuge can only hold 4 of these at a time. So we'll go over to centrifuge right here. So
Are you
look at
doing a
this.
specific RPM?
As long as you go above around 3,000-ish, you should be fine. So for this one, we can go all the way up to like 6,000 RPM, all the way up here. I just go all the way, just to ensure we crash out everything. So as I said earlier, with the anti-solvent, it'll flocculate and crash. So I haven't even shaken this centrifuge, but if you look carefully, you can already see the anti-solvent crashing out these, or flocculating out these nanocrystals here. All right, that's what the anti-solvent does. It'll crash out due to the polarity differences of your nanocrystal to the anti-solvent. So shake it up a little bit. Over here. Shake. And we'll go for about 5 minutes. We're gonna do that for this one. For this set, and if you remember, we still have half of it remaining. So it'll be a total of 4 times for the last. You'll do the same thing again. Right. Zuriel mentioned you can use distillation to recycle the hexane velocity you guys use. Yeah, that's perfectly fine. You can reuse the solvent, anti-solvent. That won't change anything about the nanocrystals themselves. But once you're done with the DMSO dropwise addition, that's it. You're all done. Whatever you use for the wash-up, as long as it's a good combination of solvent and anti-solvent, you'll get the same results. Let's go. Here. So as you can see, now it's really just a waiting game with a lot of centrifugation. If you have a centrifuge that can hold 8 of these at once, that'd be really nice. You'll have your wash-up time. Unfortunately, we only have one that is full, so we need to keep on. Any other questions so far?
Not right now. You're doing a great job explaining everything. Thank you.
Okay. Yeah. So after this first wash is done, Zuriel, I think we'll end it there because I don't think this recording should go too long because the next step with the wash up is exactly the same thing. If you follow the SOP, it's just the hexane ethanol instead. So once you're done with all the DMSO, now you move on to hexane ethanol as your anti-solvent salt combination. You do the same thing twice. Crash, dry it, it's good to go.
Okay.
Yeah. Once the step is over, apply the same concept to the hexane ethanol wash, and it's the exact same thing. I do want to show you the oh, yes. So you see how it crashes out?
Maybe beside it. There we go.
So you see how you have the anti-solvent up here, but the actual crystals down here. So even that's what, if you have a good anti-solvent, that's what'll happen. It'll crash up and
So pretty much the crystals are starting to settle already.
Yeah, they are.
yeah. Sorry, very hard to hear because of the next sentence. About 2 more minutes. Philippe have a question? Oh, okay. Don't worry, Philippe. Yeah, this will be recorded. So for you guys, you have the SOP, you have all of the, you know what you have to get, you know what materials you need, and then you'll have this recording for the first half. And Zuriel, you plan on coming here to Seattle soon, so you'll be able to see it in person yourself.
Yes, definitely. It's part of the program. I actually have to do at least a summer over there. So I'm thinking hopefully next year I'll be able to hang out with you guys.
Yeah, awesome. For sure. Hopefully by summer next year, all the COVID stuff will finally be over. I'm kind of hopeful. All right, so the first one, I want to show you what happens. You'll have the trash nanocrystals at the bottom, and the top liquid layer called the eluent at the top. And we're going to dispose of the eluent and then refill this with the nanocrystals in the flask.
Use the brakes.
Stop it. Okay. Now, what do we get here? You have your crash nanocrystals. You have your crash nanocrystals at the bottom here. All of the anti-solvent here at the top, DMSO as well. So you're crashing out all the nanocrystals, which is what the anti-solvent here does. Centrifuge, crash them out the bottom here. Sounds good too. All right. Now to save time, I'm going to start centrifuging these next four. Right? Same thing again. About 5 minutes. All right. We're going to dispose of these guys. So these are stuck at the bottom. Don't worry. You just pour it out like this. Nice salt here. Notice how it's still kind of gel-like here? That's the DMSO we still have, all right? So that's why we do the hexane ethanol wash, to kind of get rid of the DMSO. So we only have to worry about evaporating out hexane ethanol later, which has much lower boiling points. You could try to evaporate this, except DMSO's boiling point is like almost 200, and it's plastic, and you don't want to melt this guy, right? So very difficult to do that.
Have you done like experiments to see like how much hexane it actually cleans it? Like, you know, I know you're using excess to make sure that they come out really clean, but have you done like experiments where you use half the amount or a quarter of the amount and see if that affects?
So I've seen some combinations, hexane and ethanol. You want to put about at least 3 times as much hexane as ethanol. That's my experience. If you don't put that much relative hexane and ethanol, it won't crash out that well. That's just my experience with doing the second half of washing. So again, we still have about 400 mils here. So I'm going to get these guys ready for their second wash. Right? So remember, I already have nanocrystals here, but I'm adding more in here. So when I centrifuge again, I'll have a bigger layer at the bottom. That's good. Sit there for a while. This will be the second set of things. We have about 200 mils left in here. So once that's done, or put that.
Yeah, is there a reason why you continue spinning the other batch?
Why do you keep stirring the other beakers or the other glass?
Oh, just to make sure it doesn't crash out. Because remember that's the anti-solvent, so if you don't stir it, it'll crash out. So it's kind of annoying to deal with if you don't have it constantly stirring.
It's easier to pour.
So, sorry, I have to get the.
You said you centrifuge for 5 minutes, right?
Yeah, at least 5 minutes. Yeah, this is definitely the most boring part. Since it's, all the fun, cool stuff is when you saw it turn from purple to blue. This is just a lot of work.
Yeah, I guess you're kind of stuck with whatever centrifuge size you have. So
So if you guys
Yeah.
have one that can hold up to like 8 Falcon tubes of this size, that's really great. You can save yourself a lot of time.
yeah, I think we have one that holds 16, so we might be able to do all the tubes at once.
Nice, that's awesome. If anything, then I recommend using 16 Falcon tubes then because you'll have less nanocrystals per Falcon tube, so it'll be easier to redissolve and redisperse the ethanol when you do the hexane crushing. 8 should still work, but in terms of just how much volume you're limited by, I definitely recommend spreading out those nanocrystals. Oh, I forgot. So yeah, this is our next batch, the second one. We'll just shake it up a bit. Remember, we already have nanocrystals here. So whatever nanocrystals here are going to get crashed out is going to form a layer, a bigger layer here. So we're crashing out all these guys up to here. Now we'll pour out these guys. Yeah. Now we should pour out the remaining. Yeah, so if we do still have the stir bar here, we want to be careful when we pour it. We actually don't want the stir bar to fall into the Falcon tube. So we want to be a bit careful. Right, values. If you fall short, guys, on this last one, don't worry. You can fill it up with ethanol to 50 to even it out. Okay, so I obviously fell short. So, but I want to make these weights even. So I'm going to add some ethanol here. Crash out. So now, oh, and now we wait. So as you can see, this only takes about 1 hour so far. It's a very fast synthesis and very overall. It's just with the workup and stuff, that takes up like all the majority of the time. Well, as you guys said, since you have a bigger centrifuge, you guys will able to do this even faster than I ever did. Good.
Somebody else suggested using like or one of those filters and like washing them that way, but I'm thinking that it may be the powders may be too fine to be filtered. What do you think?
Yeah, you could use something like vacuum filtration or something of that nature to really clean it out. That should also work. I've been using a hot plate to burn off the excess hexane and ethanol at the very end to ensure we only have the zinc oxide. So,
Yeah, just thinking of ways to try to get the wash cycle done quicker. Seems like this is the longest.
Okay, I think you can just filter and not use the centrifugation.
ooh, no. Because the zinc oxide is condensed in the end. And so the reason you do add the solvent is because you want to crash it out of the system. That's what you do. If you're talking about the very end, you also want to do hexane ethanol centrifuge because you want to get rid of any of the reeds, so for any excess liquids. But you could do a vacuum filtration after all that if you want to do an extra wash or to dry off any excess so that you only have powder. So now it's a bigger layer here since we have deposited more nanocrystals in the remaining amount. So now we just get this thick layer here. Same with this one. This one. And this one right here. Right? So now we have one more step. We need to crash out these nanocrystals to the advance. All right, what's up? Oh, actually, sir, in your case, you only want dry powders. Yeah, you could just vacuum filtrate it. Once you get all the solid, you could wash off all the DMSO using it with ethyl acetate washes, and then just keep on vacuum filtrating to like get just the dry powder. If all you want is the dry powder solution.
Okay, yeah, we'll give that a try.
All right. So in your case, Uriel, at this step, once that's done, you have 8 of these tubes like this. You could scoop them out, put them in a vacuum filter through a funnel, just run the vacuum, keep on washing with ethyl acetate over and over. And you keep on vacuuming it out. And then eventually you just get the dry powders. So you can try that method. It might save you some time. And once that's done, pour it out, it'll be another thing you could do, Zuriel. You could, if you don't want to do the hexane ethanol washes, since you only want dry powders, you could, once you do a little bit of drying in the hood, you scrape out all the solid, put it in a glass vial, and then you heat it on a hot plate to like 250 degrees C or something like that. And then just dry off all the excess DMSO and ethyl acetate and so on. You can do that as well.
So instead of, so you're saying skipping the centrifuging stage and just going straight to this?
If you don't want to do the hexane ethanol washes, if you don't care so much about solution chemistry, but more about just getting dry powders, once this is done with the DMSO crashes, you can dry it in a hood for a bit, scrape out the solid in the Falcon tubes, put it all in like a 20 to like 50 ml glass vial, and then just heat it on a hot plate and for like 250 degrees C and like burn off all the DMSO remaining.
So the initial solution after touching out, you can't just skip the initial wash.
No, because you have nanocrystal and DMSO, so you want to crash out
the DMSO wants to go through the filter though, and then get rid of it that way.
Zuriel, you could give that a shot. I'm not too confident about it, but you could try once it's synthesized, just doing the vacuum filtration to get the powders like that.
Okay, so then pretty much after I crashed out the crystals, I could vacuum filter it and then put it in a hot plate and then get rid of all the DMSO and any other solvent in there that way.
Or as you mentioned, Zuriel, if you want to try it, since you only want the dry powders, as soon as we finish the synthesis in the hood, just pour that through a vacuum filter flask and see if you just get the powder alone.
Without the ethyl acetate.
Yeah, without the ethyl acetate. I'm a little hesitant about that because I do prefer doing some washes to clear off some ligands, but if that works for you, that'll save you a lot of time and effort. And of course, that means you don't have to waste a lot of money and effort on hexane, ethanol, ethyl acetate. You would just finish your synthesis in DMSO, pour it through the vacuum filter, dry it out, and if all you have are the powders on top, then you're good to go.
Okay, yeah, pretty much just burn off the DMSO.
Yeah, the DMSO is non-negotiable. That is the polar aprotic solvent you need for this synthesis. Very good. But if you can skip the ethyl acetate, hexane, ethanol, if you don't need any of that, more power to you. Just saves you so much on time, money, and resources.
I'll give it a try. So you're actually trying to keep these colloidal in your case, right? You're trying to keep these in
Yeah.
solution.
As you mentioned, you only want dry powders. So if you don't care about the colloidal stability and stuff, just do it your way. With the vacuum.
Okay. Yeah, perfect. Yeah, because we're pretty much gonna try to do a atomic layer deposition on the dry powder. That's the goal. So I might not need to do all that. I'm gonna give it a try to see if we can save ourselves some time.
Because trust me, when I scaled this up, I was really surprised at how much ethyl acetate and hexane and ethanol I had to eat through every time. So if you guys don't have to do that, definitely do it that way. Oh no, this one cracked. Okay.
They're taking out of the.
Yeah. So this must have been a bad falcon. So unfortunately, yeah, this one cracked. No, this has never happened to me before. So this shouldn't have happened, guys. These falcon tubes can hold organic solvents. I don't know why this one cracked, but
Probably just a manufacturing defect.
yeah, sometimes that happens. But anyways, the other three are good. I'll make sure to clean these. But yeah, you have all your other remaining ones here. And that's another reason too, Zero. If you just vacuum filtrate it, you won't get random mishaps like these. Sometimes this can happen. Well, it's never happened to me before. But I'll make sure to clean that later. Okay, so we have 7 tubes remaining, and that is basically it. You are done with the synthesis and the DMSO ethyl acetate washes. Again, in your case, Uriel, try the vacuum filtration immediately after the synthesis, and also try it after a DMSO ethyl acetate wash. Try it both ways. See, compare those two results. See what you get. If they're good, then don't even bother doing the hexane ethanol washes. You're good to go, just immediately.
All right, that sounds great. I'm gonna give that a try.
Yeah, so try those 2 ways. One way with just DMSO synthesis and then directly vacuum filtrate. Another way, try the washes I just did and then vacuum filtrate. And then just compare those results. See what you get.
Okay, yeah, we'll do that, and we'll characterize it, and we'll share notes.
All right, awesome. Okay, Professor Banerjee, Zuriel, any other questions?
No, I think that was great. We're gonna add this to the Prem folder and train all the other generations.
So all the other undergrads who weren't unfortunately unable to attend, they should definitely watch this video. We're gonna do it. Yes, please make sure also read the SOP and the papers I sent you guys. Those 2 papers are very helpful, especially the nickel and cobalt doped one. That's the most important paper to follow.
I read both of those papers, actually. I remembered one of them said that if you heat up the reaction, then it happens quicker.
Yes, you'll have faster reaction kinetics. In my case, though, I don't really care so much about heating it. I just don't have to. As long as I just got the colloidal nanocrystals, then I'm happy either way. For you guys with the dry powders, it shouldn't matter too much either. As long as you just get those cobalt zinc oxide in powder form, you'll get the same crystal structure, T, and absorption regardless.
All right, sounds great. Well, thank you for taking the time and getting this done. We appreciate you.
Yes. Let me know those results, those 2 results you get. And if those work out for you, awesome. You know, we just save ourselves a lot of time, money, and resources.
Yes, we'll be in touch soon.
Yes. Talk to you
All right.
Zuriel.
Thank you. Have a good rest of your day.
You too, Zuriel. You too, Professor Banerjee.
Bye.